Okay, the next topic we're going to discuss is sociodynamics, which describes itself as a general framework for mathematical modelling in the social sciences, and we're working in the social sciences. So how does that work? Well, according to sociodynamics, it imagines a society as being characterised by various behaviours. So we could imagine behaviours, for example, political loyalties. So people could support right-wing parties, left-wing parties, or centrist parties, let's say. Or these could be different religions, or they could be different occupations, any kind of behaviours that people might exhibit in society. But we'll focus on this one of political behaviour. And then in a society, let's imagine a society of 30 people just for convenience, there would be a certain number of people exhibiting each behaviour. So we could have, an even split between them of 10, 10 and 10. And then the idea is that at a later time this might change in some way. So one of the leftists might become a rightist, and so the configuration will change. So a particular allocation of people to behaviours, numbers of people to behaviours, is a particular state of society, and social change involves transitions between these behaviours. And it all depends on the probability of a transition. And that is going to depend on the start state and the end state. That's the end state, that's the start state. So I should have written that somewhere different. If that's the end state, then it depends on this probability, which itself depends upon both the end state and the start state. And the way in sociodynamics tends to be written is, if you're transitioning from a start state to an end state, they write the start state first. They write the start state last. So this means you're going from that start to that end. And this probability is about whether, the chance of transforming if you're in that state to that state. And the way the modelling works then is to define a whole set of probabilities for all the different possible start and end states, and then to put all this into a computer and evolve the model and see how see where you end up. Well, and not necessarily running it in a computer, it's possible to play around and analyse the equations and extract some broad properties of behaviour of a particular system, given your defined probabilities of a transition. And this sociodynamics, it involves structure and agency, because the agency is the individual changes in behaviour, but the probability depends on the whole states of the whole system. So it depends on the structures. So the structure, the overall state of the system affects the individual behaviours as transitioning from one to another. And some examples of how this has been used. Migration of interacting populations. So this studies things like different populations coming into contact, things like ethnic conflict and the causes of genocides. It's been used to study the rise and fall of different kinds of social groups. So the rise and fall of political parties, the rise and fall of religions as people, transition through these states depending on the overall state of the system. Opinion formation at political transitions. X, I use X for transitions. So things like the rise of Hitler. How did attitudes shift? These political opinions shifted to support for Hitler, and how did that happen? And another example is urban evolution and population pressure. So things like people in response to population pressure moving from the land into the city looking for work, for example. Again, this can be modelled in terms of behavioural transitions and how the individual adjusts from, say, working on the land to deciding to move to the city is dependent on the overall structure of how everybody as a whole is behaving. It can either influence them to go to the city or deter them, and that's what's built into the weights, the probabilities of transition. So you can see from these examples then that this framework of sociodynamics is relevant to the kinds of things that might be of interest to theoretical historians. And although we won't be using it in this course for any particular applications, it's certainly something we should have in our toolkit to know about as a potential approach that we could use when to solve problems that we might come across in future. Okay, so let's have a look back at our example then of a society with these three behaviours of supporting the right, supporting the left, and supporting the centre. And we can have 10 people in each category here, which can transition to 11, 9, and 10. We can describe this state of society as a vector. So this would be the vector 10, 10, 10, where 10 is the number of people supporting the right, 10 again is the number of people supporting the left, and that's 10 is the number of people supporting the centre. And this vector would be 11, 9, 10. And again, that's the number R, L, and C. And we summarise that vector as n. And to show it's a vector, we underline the little n. And this one, where one person has moved from left to right, is written in the sociodynamics framework as N R, should be N subscript R L. That means from n, we've changed to n where one person has moved from left to right. So we've gone in that direction from n to NRL. Left to right. One person has moved left to right. And from this configuration, we could go back in the opposite direction as well. We could go from NRL and end up at n. And then we said that we're interested in the probabilities of these transitions occurring. And so these are the weights attached to these possible transitions. So given the symbol W, and this would be WRL, and it depends upon the state you're transitioning to. So you're transitioning to, and I said before that the state you're transitioning to comes first, so you're transitioning to NRL from the state N. So you're transitioning to NRL from N. So and that the probability of that transition is WRL. And then this reverse transition is going to be WRL, because it also depends on what RL is going to be the transition from NRL to N. So you end up at N and you come from a state configuration NRL. So we've got these two transition probabilities, and we're interested in the rate at which this state changes to that state. So, or at least we're interested in the rate of change of the probability of being in this state. So we define these WRLs as not just probabilities of transition, but probabilities per unit time. So, you know, if the system is in this state, what's the probability per year of one person switching from being a left-wing to a right-wing supporter? So it's a probability per unit time. So to find, we also define, should say, the probability of being in state N. So that's a prob that this that's a probability of the society being in state N, and we're interested in the rate of change of that probability over time as we consider how does political opinion shift. Well, we can see from here then that it's going to be people are going to be or the society is going to be moving into that state dependent on this rate here. It's the people shifting from state NRL into N. So that will increase the probability, and it will increase it's a probability per year or per unit time of transition, the rate of at which people are likely to change from that state to that state. So it's WRL times NRL. And we'll put a plus sign because that will increase the probability of being in here if you're transitioning like that. We also need to take account assuming that people are in that state to begin with. So we multiply by the probability of actually being in state NRL. So the probability that people are transitioning like this is the probability that they're in that state to begin with times the probability that they then transition into this one. So that will add to it, and we will take away the transitioning in the other direction. So that's WRL, NRL, N is moving in that direction, is reducing the probability, because this is shifting out of it, multiplied by the probability that you were in that state to begin with again. So you're assuming you are in that state, and which is just P of N. But this isn't the only way you could change out of that state. We could have another configuration where we shift from this state not by someone from the left moving to support the right, but someone from the left moving to support the centre, which would then become NCL, shifting from the left to the centre. So in that case, the people supporting the right wing wouldn't change, but now a leftist has changed to the centre, so the left has gone to 9, and that has, the centre has increased to 11. So we could go like that as well. And in this case then we would write the well, let me be consistent and just put the arrows the same way round. So moving towards that is on the top, so we'll write WCL this time, of moving into state N from this configuration NCL. That's the probability of transition in that direction, and then in this direction it's WCL again. It depends on the configuration we're talking about. NCL moving into NCL from N. So if we want to find dPm by dt, we've taken into account those two flows, but we've also got another flow here in and out of this state. So we would also add in that probability of moving into state N from NCL times the probability now that you are in that state NCL. And here we'd have to subtract WCL of NCL N times the probability that you're in state N. That's that flow out of this state. And there are also other configurations as well. We could have someone from the right moving to the centre, or someone from the centre moving to the right, and so on. So there were many combinations that we haven't yet considered, but we would have to add those in as well, some increasing and some decreasing. And instead of thinking in terms of right, left and centre, we can change all this just into just number them to make it more general. So we'll call that state 1, state 2, or behaviour 1, behaviour 2, behaviour 3. And all these R's and L's would then change accordingly. So let me fill those all in. Okay, so what I've done is changed all the R, L and C's for right, left and centre into more generic behaviours 1, 2 and 3. And we could imagine that in general there would be a lot more behaviours, so 4, 5, 6 and so on. And so I've updated this as well with the 1, 2s and 3s, and we can now write this more generally by saying that it's going to be the sum of all the possible combinations, 1 and 2, 1 and 3, 2 and 3, 2 to 1, 3 to 1, etc. So it's going to be the sum of Wij times n of Nij times P of Nij over all the possible values of I and j. So that's plus, and then it's minus this, again, the sum over all the possible values of I and j that we could put in here instead of 1 and 2, 2 and 1, 3 and 2, 3 and 1, etc. So that's Wij into Nij to n times P of n. And this is then the basic idea of sociodynamics. This is dp by dt of n. We're defining a society in terms of its state, in terms of the distribution of people among these behaviours, and we've then got this formula for the rate of change of the probabilities of being in all the different states dependent on these transition probabilities or weights that we assign to these transitions. So while that's the basic idea for sociodynamics, it doesn't quite stop there. The first refinement is to recognise that there are different categories of people. So, for example, the most basic one is male and female, or it could be different religions, you know, Protestant, Catholics, and other religions. So we're not just interested in how many people support each behaviour, but we're interested in how many of each category of people support each behaviour. We want to distinguish between how many males support the right wing versus how many males support the left wing, and also how many females support the right wing and how many females support the left wing. We want to take into account how that differs by the category of person. So our vector describing the state of the society n is going to be the number supporting the right wing of males. Let's say, if we just stick with that example of the category, so that's written as a superscript, the category of person, then the number supporting the left wing, males, the number supporting the centre, males, and then the same for females. So our state vector has got this extra complication now of having this superscript to represent the category of person. And if we put this in generic terms, so replacing the subscripts and superscripts with numbers, so we've got behaviour 1, category 1, behaviour 2, category 1, up to NC, where C is the number of different behaviours, all for category 1. And then we'd have some more, and then we'd have then N1 up to NC for category alpha, and then we'd have some more, and then we'd have N1 up to NC for category P, where there's a total of P categories. So this is, you know, our state vector describing the society could get very long and complicated. And with this, then, the equation for the change of the state, dp by dt of n, Before we just had the sum over I and j, but now we've got to take into account alpha, the different categories of people as well. So it looks like whereas before we had wij, we've now got wij alpha, and these are the plus ones. So this is moving into state M from the state nij alpha, and times the probability of being in the state nij alpha, and then minus the sum over ij alpha of wij alpha, nij alpha, n times the probability of being in state n. That's the people moving out into this other state, nij alpha, superscript alpha. But sociodynamics doesn't stop here either. We also add two other categories of variables. So here we've considered the number of people exhibiting particular behaviours. The next thing, sociodynamics considers the idea of material variables, so describing the material state of a society, material state of a society. So these might be things like the economic output of the society. It might be the number of buildings in the society. It might be the length of the roads built by the society. So these are material variables describing the society. And in this case, the transitions can be just adding or subtracting one to each material variable. So we could go to mk plus 1. So adding 1 to the kth material variable, that's written, if that's state m, this is written as state mk plus. And similarly we can have subtracting 1 from the kth variable is mk minus. So we once again have flows out of this state. If it's in that state, it can flow with probabilities of transition to mk plus or mk minus from state m, and it can also flow from either of those states back into this one from those. This should be wk. Depends on the state we're talking about. So we've got those flows in and out, similar to what we had before, though the detail of how we describe these weights is slightly different. And then lastly, we take into account people's inner states, their inner thoughts and feelings. So people might be exhibiting a particular behaviour, but they might have different reasons for exhibiting that behaviour, or different reasons for supporting the right-wing parties, or they might have different levels of commitment to supporting that party or exhibiting that behaviour in general. And that's important, when we're considering about the chances of people transitioning from the states, from one state to another, or one behaviour to another. It's not just their behaviours, what their behaviour actually is that affects it, but also their inner thoughts and feelings about their behaviour. So that is another vector, which is represented with the letter theta. And in that case, we have something similar to the number of people exhibiting the behaviour. It's the number of people having each inner state. So there will be the first state up to nth state, and that will be for the first category of person, and then we'll have theta 1 up to the nth state for the second category of person, and so on up to theta n of p, where there are p categories of people and n possible inner states that they could have. And this then gives us a state with the we talk about the probability of the state, which is determined in terms of the particular values of the material variables, the distribution of people among the different possible behaviours, and this vector theta, the distribution of people among the different possible inner states. And it also depends on time. That probability will change over time. That's what we're interested in, seeing how that probability changes over time as these transition probabilities apply and cause people to move from one state to the next. So putting all that together results in a rather complicated equation, which I'll write up. Okay, so this is the equation that you end up with. So there's the first one for the material variables when we considered adding or subtracting one from the kth state. So we've got a positive contribution from ones coming from the states of plus or minus 1 into this state, and taking away the ones that are in this state and going out to either the plus or minus 1 of the kth material variable. Here's the equation we constructed earlier for the number of people in each behaviour. So people moving from another configuration into this configuration of behaviours, and taking away the people in this configuration of behaviours moving out again, or the probability of being in that behaviour, being in that overall state of behaviours out to a different state of behaviours. And then lastly, this is for the inner thoughts and personal variables, where it's kind of a combination of the two. Here we imagine those personal states as increasing or decreasing by 1, so we can go to the a greater intensity of feeling or a lesser intensity of feeling from the existing intensity. So we've got I plus or minus, I plus or minus here. So there's people in this case moving into this state from above or below, becoming either less intense from the more intense state or more intense from the less intense state. And then there's people moving out of it, or the possibility of moving out of it from this state to becoming more or less intense. And this is called the master equation. The idea is then to see how it behaves based on assumptions that you make for these weights. And while this looks incredibly complicated, it turns out that in fact it often is just some of the variables that dominate the behavior. So you as you analyze this, you pick out which things are really important, and that's a process known as entrainment. So I'll just use this bit of space here, entrainment. Which is about the idea that some of the variables just follow the others. So their contribution isn't really important. Their behaviour is determined by these dominant variables. And how that works is because there is fast and slow variation in the variables. Some variables respond quickly and others respond more slowly, and it's the slow ones that tend to dominate. And I'll just give you an example here of population growth against time. Human population can grow exponentially, it can grow very fast, but it's constrained by the carrying capacity, the number of people that can be supported given your available technology and other factors like land and resources. But so the capacity might increase more slowly like that, say in a linear way. Your population can grow exponentially very quickly, and because it can grow exponentially but can't go beyond what can be supported, it will always bump along behind this capacity. So population, the growth of population, you don't really need to model that, the details of this exponential growth, because it is just constrained or entrained by the slow growth of capacity. So population just tracks capacity. So you can neglect population and just focus on the dynamics of capacity. And the same applies with this master equation. Once you start populating this with weights to represent a particular scenario, you'll find that some of them are responding quickly like population, and there are just a few that respond slowly, and it's those slow ones, the dominant variables, that you focus on. So that's the basic ideas of sociodynamics. That's kind of the flavour for what it's doing, which is sufficient for this introductory course on theoretical history. So it's it's something we should be aware of, certainly at an introductory level. But sociodynamics is a field in its own right. You can see it's potentially rather complicated, and so it's something that would be of interest for theoretical historians who want to pursue this particular approach. But it's not necessarily something that at an introductory level we want to get into in huge detail. But I've given you a flavour for it. It's out there, and if you find that interesting, you can follow that up.